So very good morning to everyone. So it's a very long time that we had a class and we had an interaction with you guys. It's been a very long, but the institution have took up a very great step in bringing you, in diagnosing, or I would say in rectifying the method of learning the P block elements too through a study material. And it's very clear that it is not possible to study the all inorganic reactions just by harding it, and we cannot just memorize the formula, the molecular formula of the reagents, reactants and the products and all. So the better way to study is learning this reactions through the sentences is the only way. So this P block elements too, with this material, it is very so sophisticated that we could bring you up so that you can learn in a better way. We'll go with it. In the P block elements 1, which we have seen in the unit 2, completely talks about the boron family and the carbon family. So after which the P block elements 2 has the rest of the family, which includes from the group 13 to group 18. So to begin with, the group 13, which is the nitrogen family. See, nitrogen belongs to the group 15, and the other name of the nitrogen is, the family is called as nitrogens. It's very clear that, and we have seen it in the unit 2 itself. Its occurrence, if you look into it, about 78% of the Earth atmosphere contains the nitrogen in the gaseous state. So that is what it is mentioned. And in the form of a compound, nitrogen exists in the form of a Indian salpeter and child salpeter as KNO2 and NaNO2. Then phosphorus is the most, I would say, the 11th most abundant element, and it exists in the form of a phosphate as fluorapatite, chloropatite, hydroxyapatite. The molecular formula of the fluorapatite is Ca5PO4 thrice, and the chloropatite is Ca5PO4 thrice Cl. There it is F, and here it is the twice of the Ca5, which is CF10PO4 6 times, OH twice, hydroxyapatite. Then the rest of the elements of the family like arsenic, antimony, bismuth, which exists in the form of sulfides, along with the phosphates which has been extracted. Right. This is what its occurrence. So to summarize with, nitrogen, it is the 78% of composition which is present in the air, then followed by in the form of a compounds, it exists as an Indian salpeter and child salpeter, which is with the molecular formula KNO2 and NaNO2. Then phosphate, its occurrence in the form, it is the 11th most abundant element, and it exists in the form of a fluorapatite, chloropatite, hydroxyapatite. Fluorapatite has a molecular formula Ca5PO4 thrice F, chloropatite has a molecular formula Ca5PO4 thrice Cl, and hydroxyapatite has a molecular formula Ca10PO4 6 times and OH twice. So this is what. The rest of the elements, antimony, bismuth, arsenic, exists in the form of sulfide, which is not at all abundant there. So it's not at all abundant there. It is very clear. Then, looking into its physical properties. If you look into the physical properties, nitrogen exists as a gas at the room temperature, which is 298 Kelvin. The rest of the elements exist in the form of a solid, no doubt in that. Then, atomic number, obviously, if you look into the group, because it's belong to the same group, nitrogen, phosphorus, arsenic, antimony, bismuth, atomic number will definitely increases from nitrogen to the bismuth. Then, if you look into the isotopes which is exhibited by these elements, nitrogen exists as an N14 and N15, phosphorus exists as P31, the rest of the elements exist in its own state, which is arsenic 75, then antimony 121, bismuth is 209 with the molecular mass. Regarding that, atomic weight. Then, the atomic mass, atomic radius, density, melting point, boiling point, everything increases from nitrogen to bismuth. So obviously it increases, right? Because when the number of protons, number of electrons increases, obviously the mass also increases. Down a group, atomic radius will increase, no doubt in that. As the mass increases, density, melting point, boiling point will definitely increases. There are certain variations if you look into the group. Those are all because of the complicated crystal lattice structure. It is only because of the crystal lattice structure, none other reason has been found. Then arsenic has an ability to get sublime, which means it can convert the solid state into its vapor form at the 889 Kelvin. So this is regarding the physical properties. Now coming back to the preparation of this regarding the electronic configuration. Electronic configuration is very easy to learn. If you list out the elements of the group, it is nitrogen, phosphorus, arsenic, antimony, bismuth. Nitrogen with the atomic number 7, you need to add 8 to that. So obviously phosphorus will get 15. Again, you need to add 8 into that. Arsenic will get 33. Again, you need to add 8 into that. So antimony will get 51. Again, you need to add 32 to that. So therefore, bismuth will have an atomic number of 83. So to write the electronic configuration by enclosing the inert gas configuration. So starts with the helium, neon, argon, krypton, xenon. Till xenon it is enough for writing the bismuth. Then the valential electronic configuration, the general electronic configuration for this family is ns2np3. So starts with 2s2 2p3, 3s2 3p3, 4s2 4p3, 5s2 5p3, 6s2 6p3. Then before 4s 3d comes. So 3d10. Before 5s 4d comes. So 4d10. Then before 6s 4f comes and 5d comes. So 4f14 and 5d10. Coming again, see, before 4s it comes 3d. Before 5s it comes 4d. Before 6s it comes 4f and 5d. So you need to enclose all these things while writing the electronic configuration, having the basic things in the mind. You need to increase the atomic number by adding 8, 18, 18, 32. Likewise. Then by enclosing the noble gas configuration, helium, neon, argon, krypton, xenon, etc. Then the general outermost electronic configuration ns2np3. So starts with 2s2 2p3, 3s2 3p3, 4s2 4p3, etc. Then before 4s 3d comes, 5s 4d comes, 6s 4f and 5d comes. That's all. Now coming to the preparation of this nitrogen. So it's a principal gas in the atmosphere because it occupies 78% by volume. We know it. And how it has been prepared in the industries by the fractional distillation of the liquid air. Liquid air contains a mixture of an O2 and N2. Then while doing the fractional distillation, we know that oxygen distills out at a different temperature, nitrogen distills out at a different temperature. So obviously it is very easy to separate through the fractional distillation here. Then the second method is thermal decomposition of the sodium azide. Sodium azide has a molecular formula NaN3. NaN3. If we heat it at 575 Kelvin, it decomposes to form sodium and nitrogen gas. So to balance with, I will make it as 2 here, I will make it as 2 here, I will make it as 3 here. So this is regarding to balancing. So it's a decomposition of the sodium azide. Then the second one is you can able to oxidize the ammonia to get ammonium so that you will be able to get the nitrogen gas. Let's check it out. Ammonia reacts with bromine and forms ammonium bromide. Here the oxidation state of the nitrogen is 0. Here obviously it should be +1. So it has undergone oxidation. That's why it is mentioned as an oxidation of ammonia using the bromine water. Now we need to balance it. So the byproduct, the main product for us is nitrogen gas. So to balance with. So how do we balance it? So if I make it as 3 here, then bromine becomes 6. So I need to make it as 6. So nitrogen becomes there 6. So I'll make it as 6. Otherwise, you can make it as an 8 here. So instead of making as 6, you can make it as an 8 here. So NH3 reacts with bromine to form NH4Br, then N2. So if you make it as 8 here, nitrogen becomes 8. So obviously I'll make it as 6 here. So bromine becomes 6. So I'll make it as 3 here. So hydrogen is 8 3s are 24, 6 4s are 24. Equation is completely balanced. Since we are rushing up or we are trying to bring it out a collection of a content in a single video, it is a better way to directly go to the stoichiometry and finish it off. Now, so this is the methods of preparation. So totally 3 methods: industrial methods of preparation by the fractional distillation of the liquid air, then the second method by the thermal decomposition of the sodium azide by heating at 575 Kelvin, then by the oxidizing the ammonia with the help of a bromine water, we will get the third one. Now, next one. Properties. See, nitrogen is highly stable. So it is not capable of reacting spontaneously. So it's an inert. It has a high bonding energy, which means it is very difficult to break the bond existing between the nitrogen. So the bond energy between them could be 225 calories per mole or 965 kilocalories per mole in terms of an energy we would represent. The terrestrial nitrogen, which means the nitrogen which is present in the desert area, 14.5% will exist in the form of a nitrogen 14 and 0.4% will exist in the form of an N15. So this is what we could able to find in the desert regions. That's what it is mentioned as a terrestrial nitrogen. N15 is used for an isotopic labeling. If we are trying to, let us assume that plants has an ability to consume the nitrogen. In order to find out at what particular time how much of nitrogen have been consumed, we need to supply this N15 and N15 so that we can able to trace how much of a nitrogen have been consumed by the plant in a particular time. So this is what isotopic labeling regarding this. The next one is, it is less reactive, as I said, since it is an inert, it will not capable of reacting so easily. Because it is a triply bonded species, very difficult to break the bond between them. So that, see, even though it's a triply bonded and nitrogen has a lone pair of electron over its head, it is cannot act as a donor because it is already stable. So it will not react so easily. That's why it cannot act as a donor. Whereas if you look into the other triply bonded species, which is like carbon triple bond carbon, carbon triple bond double bond oxygen, then carbon triple bond nitrogen, nitrogen triple bonded carbon, carbon triple bonded nitrogen, etc. These are all has an ability to donate an electron and get stabilized. But nitrogen here doesn't need anything to get stabilized further because it is already inert. So that is the reason. The next one, what's the reason behind comparing the rest of the elements, rest of the triply bonded species is because they are all isoelectronic, which means the electronic, the number of an electrons is almost similar. So that's why it is considered as an isoelectronic. The last one, nitrogen can form a complexes with the metal like carbon monoxide. See, we have already seen in the metal carbonyls. In metal carbonyl, carbon monoxide acts as a ligand. So N2 also can here, look into it, back bonding takes place here, where in the metallic carbonyl, first carbon monoxide will donate an electron to the metal and the electron density of the metal increases, so that metal will donate a pair of an electron from its d orbital to the ligand. So this is regarding the back bonding. It donates electron to the pi star orbital of the carbon monoxide. Similarly, for nitrogen also, it has a nitrogen can form complexes with the metals like cobalt. Okay, as like a carbon monoxide, it has also ability to act as a donor. See, it donates an electron to the metal. When it donates an electron to the metal, the electron density increases. So immediately metal will give electron back to the nitrogen. So that is what here it is mentioned as a back bonding. The coordinate bond that has been formed. Next one, chemical properties. Chemical properties is lithium reacts with the nitrogen at the room temperature and forms lithium nitride, Li3N. So to balance with, I'll make it as 2, I'll make it as 6 here. So equation is balanced. Then regarding calcium nitride, calcium will react with the nitrogen in the red hot condition to form calcium nitride, Ca3N2. So to balance with, here also it is same. So if I make it as 3, here it is an F. Then boron is capable of reacting with the nitrogen at the bright red hot condition to form boron nitride, which is Bn. The molecular formula, stoichiometry is 2 on either side. Then nitrogen, this reaction is specifically called as a Haber's process. When I say Haber's process, nitrogen reacts with an oxygen in the ratio of 1:3 to form an ammonia. Here, the formation of the reaction involves in the loss of an energy, which means it undergoes an exothermic reaction. So heat energy have been released minus 46.2 kilojoule per mole. Let's look into the reaction. See, nitrogen reacts with hydrogen. As I said, it reacts in the ratio of 1:3. It forms ammonia. The whole reaction takes place at a higher temperature and the higher pressure. Iron acts as a catalyst, molybdenum acts as a promoter here. So this is what regarding the formation of an ammonia. See, Haber's process is widely used to synthesize the ammonia industrially. So this has been mentioned as the properties of the nitrogen. Next one, reaction with oxygen. So nitrogen reacts with an oxygen and forms a nitrous oxide. And it forms nitrous oxide at a higher temperature. So nitrogen reacts with oxygen at a higher temperature of 3473 Kelvin. It forms a nitrous oxide, which is N2O. So to balance with, I'll make it as 2 here, I'll make it as 2 here. So that's it. So regarding balancing this reaction with an oxygen. So till now we have seen the formation of the nitride with lithium, formation of the nitride with calcium, formation of the nitride with boron, then synthesis of ammonia through the Haber's process, then the reaction of the nitrogen with oxygen to form the nitrous oxide. So till this we have seen. Then next one is uses of a nitrogen. Nitrogen, how it is used? We have already synthesized ammonia with the help of Haber's process. So it is used to manufacture ammonia, nitric acid, calcium cyanamide, etc. Then liquid nitrogen is used in the cryosurgery. Cryosurgery is the surgery which is done at a very low temperature in order to avoid any pathogens to get into it. So it has been done very low temperature and to safeguard the organs also. Then biological preservation. It has the ability to preserve the biological specimens and all. So that is why it is used as a biological preservative. See, I am coming again once more with the preparation. The preparation of the nitrogen includes the decomposition of the sodium azide, 1 at 575 Kelvin, then the distillation of the liquid air industrially, then oxidation of the ammonia with the help of a bromine water, 3. If you look into the chemical properties, if you look into it, it has an ability to form a nitride with boron, lithium, as well as calcium, etc. Then nitrogen reacts with the hydrogen in the ratio of the 1:3 to form ammonia. This process is called as an Haber's process, widely used industrially. Then the last one which we have seen is nitrogen has a capability to react with an oxygen at the temperature of 3473 Kelvin to form some nitrous oxide, which is N2O. Then uses of nitrogen includes the formation of the ammonia, nitric acid, cyanamide, and liquid nitrogen is widely used in cryosurgery, which I said that surgery which has been done in a very low temperature and used to preserve the biological specimens. Then next one, ammonia. Ammonia, the synthesis of an ammonia is very clear. We have seen already from the Haber's process. Then you can also able to prepare the ammonia with the help of an hydrolysis of an urea. Urea has a molecular formula NH2CO NH2. If you hydrolyze it with the help of a water, the bond breaks in this way. So oxygen goes here, H comes here, H comes here. So 2 molecules of ammonia will be getting along with carbon dioxide as a byproduct. So this is one of the method of preparation. The other method of the preparation is by reacting with this ammonium salt with the base. You can take the ammonium ion from a salt, which is NH4 plus, and from the base you can take it in the ionic form as OH minus. See, this OH minus has a tendency to abstract the NH4 hydrogen from the NH4 and goes as H2O. Then the rest of the product which has been left out is ammonia. These types of the reaction we have already seen in an ionic equilibrium. It's very clear. The conjugate acid-base pair. In such a way the reaction happens. Then the next reaction is ammonium chloride. The salt of an ammonia reacts with the calcium oxide. What happens? It's very clear. Calcium will take up the chlorine and goes as calcium chloride. Then in order to remove this oxygen, 2 of the hydrogen will take the oxygen and goes as a water molecule. Then we will be getting also 2 moles of an ammonia. So this is the reaction. So here the oxidation state of ammonia, here it is +1, the ammonium is +1, here it is 0, which means it undergoes reduction. Calcium oxide actually reduces the ammonium to ammonia. So this is what the reaction. Question may ask in any way, depends on the sentences that we study. Okay. Then magnesium nitride. Magnesium nitride has a molecular formula Mg3N2, reacts with the water to form magnesium hydroxide, which is Mg OH twice plus NH3 ammonia. So to balance with, since nitrogen is here, I'll make it as 2 here. Then magnesium is 3, I'll make it as 3 here. So totally we have a 12 hydrogen and 6 oxygen, so I'll make it as 6 here. So to balance with, that's all. So this is regarding the preparation of an ammonia. The preparation of an ammonia includes the hydrolysis of an urea. You'll be getting a 2 moles of an ammonia and 1 moles of carbon dioxide goes as a byproduct. Then you can take the salt of an ammonium to be written in an ionic form. It has to be written in NH4 plus along with the base, which is OH minus. It forms NH3 plus H2O. Then calcium oxide has an ability to reduce the ammonium ion to ammonia. So there we will be getting an ammonia with the help of a byproduct formation, calcium chloride and the water molecule. Magnesium nitride can also be hydrolyzed to form magnesium hydroxide and ammonia. So these are all the various ways to prepare to prepare ammonia. As it was discussed already, Haber's process is also one of the important reactions for the synthesis of ammonia. Industrial preparation, which we have seen previously. Industrial preparation includes the formation of ammonia. The same reaction goes like N2 plus 3H2 as it was discussed already. In reaction takes place in the ratio of 1:3. It forms an ammonia. The formation reaction is an exothermic reaction. That is why it has been mentioned as del HF in the with a sign of negative. So exothermic reaction takes place. See, in order to fasten the attainment of an equilibrium, you can use this alumina or you can use this potassium oxide. Hydrogen, the source of this hydrogen is from the water gas. The source of the nitrogen from the liquid. All this thing. See. The source of the hydrogen is very clear, it is from the water gas. For the nitrogen, which we have discussed in the preparation of the nitrogen itself, is the fractional distillation of the liquid air gives us the nitrogen. So, we will be getting as a source. Then, regarding this, properties of an ammonia. See, properties of the ammonia, it's a pungent smelling gas. It's very clear, it's a pungent smelling gas. Lighter than air, mass is very less. The air here, it talks about the oxygen. Liquefied at 9 atmosphere. We can liquefy this ammonia at the 9 atmosphere. 9 atmosphere is not an easy pressure for us to sustain and all. 9 atmosphere here, it's a high pressure actually. So therefore, this is regarding that. Then the other two physical properties is liquid ammonia boils at a very low temperature of a minus 38.4 degrees Celsius and freezes at a temperature of minus 77 degrees Celsius. So these are all the physical properties. Pungent smelling gas, lighter than air, liquefied at 9 atmosphere, boils at minus 38.4 degrees Celsius, freezes at minus 77 degrees Celsius. So this is regarding the physical properties. Now coming to the chemical properties. Liquid ammonia actually resembles the property of the water because it has an ability to form a hydrogen bonding. Regarding hydrogen bonding, I hope you are all very familiar, and regarding the water formation of hydrogen bonding, it is also very clear. Then ammonia, if you look into the solubility of an ammonia, this ammonia is actually extremely soluble in water. Like 1 mole of an ammonia can be 702 moles of an ammonia can be dissolved in 1 moles of water. Similarly, it has been mentioned in terms of volume. 702 volume of ammonia will be dissolved in 1 volume of water at a temperature by maintaining at 20 degrees Celsius and 760 millimeter of mercury pressure. Okay, 760 millimeter mercury pressure here. So that is why it is extremely soluble in water. Then when it gets soluble at a low temperature, it has been isolated in the form of 2 hydrides. One NH3.H2O, other one 2NH3.H2O. These are all soluble hydrates of an ammonia when ammonia gets dissolved in a water. So these are all the hydrates. See, obviously, when the water molecule is capable of forming hydrogen bonding, when ammonia is capable of forming hydrogen bonding, ammonia can form a hydrogen bonding with the water. So it has been isolated in the form of an hydrate. In aqueous solution, we have seen this type of a reaction in the ionic equilibrium itself. Ammonia will react with the water by abstracting a proton because NH3 has a lone pair of an electron over it. So by donating a lone pair of an electron to the proton, it has an ability to abstract a proton, it turns into NH4 plus. Then from the H2O turns into as OH minus. Then as water has an dielectric, since with the properties of the ammonia is almost similar to the water, it also has an ability to show the dielectric constant exhibited by them. Dielectric constant of an ammonia is almost good as like a water. So it's a fair good ionizing solvent as like a water. So what's its ionizing nature and how far it has been ionization takes place is stated here. If you have ammonia dissociated into NH4 plus and NH2 minus, if you look into the constant, the equilibrium constant exhibited by them at the temperature of minus 50 degrees Celsius, it is 10 power minus 30. And the equilibrium constant exhibited by the decomposition of the water leads to the formation of an H3O plus and OH minus here is 10 power minus 14 at 23 degrees Celsius, which states that it is not excellent ionizing solvent as we have seen in the water. It is a good ionizing solvent, almost similar to the water. So this question you may expect, because these are all the questions which the rest of the people may not be expect in the examination. Show that the dielectric constant of an ammonia is high, or show that ammonia is a fairly good ionizing solvent as like a water. So likewise the question is, so you have to state that it's a good ionizing solvent like a water, and by establishing this equilibrium constant expression you can able to find that. Then chemical properties. See, as nitrogen and hydrogen is capable of forming ammonia, when ammonia is heated at a higher temperature, it starts to decompose into nitrogen and hydrogen. It starts to decompose as nitrogen and hydrogen. See, this reaction actually exhibits an equilibrium. The whole dissociation will occur on a continuous sparkling, which means I need to generate this temperature which is greater than 500 degrees Celsius with the help of an electric discharge. So that continuous sparkling will definitely takes place. So complete dissociation will happen. Then reaction with an air or oxygen. Ammonia, see here, does not burns in air, but it burns the free oxygen, giving rise to an yellowish flame. See, if you have a mixture, obviously when I say air, it has a mixture of various gases, but ammonia doesn't react with all mixture. When there is a mixture of gases, it reacts with an oxygen by giving out yellowish flame. Then looking into the reaction, ammonia will react with an oxygen to form nitrogen and water. So to balance with, I will make it as 2, hydrogen here it is 3, so I will make it as 6 there, here, so I will make it as 3. So oxygen is 2 here, so 3 here, so I will make it as 3 by 2 of O2, or you can just double the stoichiometry and write it as 4 here, then here it is 3 here, then here it is 2 here, then here it is 6. You can double the stoichiometry. That way also you can able to balance it. The next one, ammonia, in the presence of a catalyst like a platinum, it reacts with an oxygen and forms nitric oxide with the molecular formula NO. So you need to specify it very clear. When ammonia reacts in the absence of the catalyst, product is nitrogen. When ammonia reacts with the oxygen in the presence of a catalyst like a platinum, the product is nitric oxide. So to balance with, so here it is 3, here it is 2. There is no other way I have to make it as 3 here. Then here I have to make it as 2 here. The nitrogen becomes 2, oxygen, nitrogen becomes 2, so I will make it as 2 here. Then here it is 5. So here it is 5 I can make it as 5 by 2. 5 by 2 of O2, or you can just double the stoichiometry and write it as. That's all. The next reaction is lead oxide. PbO plus NH3 gives Pb plus N2 plus H2O. See, lead oxide is capable of reacting with ammonia, so that it has been reduced. The oxidation state of the ammonia here it is doesn't change. Here also it is. Here it is plus 3. Here it is 0. So plus 3 is reduced to what? 0. Okay. So I let here also here it is plus 2 is reduced to 0 here. Okay. So this is regarding. So to balance with nitrogen there it is 2. So I will make it as 2 here. So we have got a 6 hydrogen. So I will make it as 3 here. So oxygen is 3 there. So I will make it as 3 here. So lead is 3. I will make it as 3 here. This is regarding the balancing of this. Then next one is reaction with an acid. See, ammonia reacts with an acid and it forms a salt. Let's take ammonia. It has been mentioned already. Ammonia reacts with an acid to form an ammonium salt. When NH3 reacts with HCl, it forms NH4Cl, or you can take any other acids like a sulfuric acid. When ammonia reacts with H2SO4, it forms NH4 twice SO4. Okay, which what this is regarding this is the affinity of ammonia towards proton is greater than the water, which means the ammonia reacts more spontaneously with the acid when compared to the water. So this is what the statement. That's why it has a great affinity to abstract the proton over there, because it is a Lewis base. It has a free electrons to get donated to the H plus, so that it can abstract the H plus. So that's one. Then reaction with the chlorine and chloride. See, reaction with the chlorine takes place. It depends on whether it's an excess ammonia or excess chlorine. Very firstly, if it is an excess ammonia, ammonia reacts with chlorine and forms nitrogen by evolving HCl. So to balance it, I'll make it as 2. So hydrogen here it is 6. So I'll make it as 6 here. So chlorine is 6 there. I'll make it as 3 here. Then the hydrochloric acid that has been formed reacts with ammonia and forms NH4Cl. You can just leave it as such, or you can just take the 6HCl and react with 6 ammonia and form 6 NH4Cl. Stoichiometrically all are same. The next one, with the excess chlorine forms an explosive substance called nitrogen trichloride, NCl3. Liquid. NH3 reacts with chlorine to form NCl3 with HCl. So to balance with chlorine here it is 3. So if I make it as 2, chlorine becomes 6. I'll make it as 3. Nitrogen becomes 2. So hydrogen becomes 6 here. Hydrogen becomes 6. So I'll make it as 6. So chlorine almost it becomes as 12 here. So I need to make it as 6 here. Okay, or you can just make it as 1 3 1 3 in the stoichiometry and leave it out. And the ammonia which has been, since it is done in an excess chlorine with the HCl, it forms NH4Cl, similarly as we have said. Okay, so firstly, if the reaction is done in an excess chlorine, it forms an explosive substance called as nitrogen trichloride. If it reacts with an excess ammonia, your product is nitrogen gas will be about, right? So that is regarding that. Next one, formation of the nitrites. Formation of the nitrites actually includes sodium reacts with ammonia to form soda amide. Soda amide with the molecular formula NaNH2 by evolving H2. So I need to balance it. So if I make it as hydrogen, there is 4. So if I make it as 2, hydrogen becomes 6. So if I make it as 2, hydrogen becomes 6, nitrogen is 2, sodium is 2. So balance, that's all. The next one, magnesium reacts with ammonia to form magnesium nitride, Mg3N2 by evolving hydrogen. So here it is 3, then here it is 2, hydrogen is 6, so I will make it as 3. So this is regarding that. So the properties, various properties here for the ammonia. Then the next one is with the metallic salt. Ammonia actually reacts with the metallic salt and it has an ability to form the metal hydroxide or the metal complexes with the copper. See, Fe3 plus reacts with ammonium ion, so NH4 plus in the presence of a base OH minus. Nothing, the ammonium ion will just come out as like that. Fe will form an hydroxide, FeOH3. So I need to make it as 3. That's all. Oxidation state of the ion is same. Then copper Ce2 plus reacts with the 4 moles of an ammonia and forms tetramine copper 2 ion, Cu NH3 4 times 2 plus. So this is regarding the tetramine copper 2 ion that has been formed by the reaction between the copper and the ammonia. Then regarding the formation of an amines. Formation of an amines actually include the dipole-dipole attraction actually, because the presence of the lone pair of an electron over the nitrogen makes it to act as a dipole, which is electron rich, right? So charge separation will actually happen here. So ammoniated compounds are formed by the dipole-dipole ion dipole interaction. Then hydration, hydrate as a hydrated salt, as the ammoniated salt, calcium chloride will take up 8 molecules of an ammonia and form CaCl2 H2O. The thing is, the negative end of the ammonia dipole is attracted to the Ca2 plus. Obviously, the negative end is nothing but the lone pair of electron over the nitrogen. So it will get attracted to the nucleus, which is Ca2 plus, and forms a bond there. Then ammonia is capable of acting as a ligand, which we have seen previously in the formation of the tetramine copper 2 ion. Here also, ammonia can form a complex with the hexamine cobalt complex and diamine silver complex, etc. Then ammonia reacts with the copper sulfate to form, which we have seen already, the tetramine copper 2 sulfate, which is a blue color, which the color of the solution is obviously blue. Then the structure of an ammonia. The structure of an ammonia, because of the lone pair of electron present over the nitrogen, makes it sp3 hybridized, as well as since it is an sp3 hybridized, we may expect the tetrahedral structure, but because of this lone pair and the bond pair repulsion, the tetrahedral angle 109.5 degree have been reduced to 107. See, usually when it is sp3, it's a tetrahedral, but there is a repulsion, additional repulsion present here between the lone pair and the bond pair. So bond angle will be reduced from 109.5 to 107 degree. The bond length between the nitrogen and the hydrogen is 1.016 angstrom. The distance between these two hydrogen is 1.645 angstrom. So bond angle is already mentioned. So nitrogen, it exists as a ammonia will expect it to be a tetrahedral structure because of lone pair and bond pair repulsion. It is not as so. It exists in the form of a pyramidal shape. So this is regarding ammonia. So in this session, we have started with the p block elements 2 and we have come up with the nitrogen. We have prepared nitrogen, we have looked in the properties of the physical and chemical properties of the nitrogen, uses of the nitrogen. Then we have started with ammonia, following by we have prepared ammonia through various methods. Physical properties we have seen, chemical properties, the question which I stated show that the dielectric constant of the ammonia is a fairly high. That question we have discussed because it's a question you may expect when the questionnaire sets like the people should not answer this kind of a question, or the The one who studied so well only has to answer this question in such a way. If the question have been taken, you can expect those questions and all. And finally, we have done with the structure of ammonia. So that's it with this session. So we'll continue with the nitric acid and rest of the compounds of the nitrogen, followed by the phosphorus and the rest of the unit in the upcoming session. Hope you enjoy the video. Thank you so much.